Hello, my name is Tuman, and today I'm going to be talking about SCONE, which is Secure Linux Containers with Intel Software Guard Extensions, or Intel SGX. This paper was done in 2016 by the authors you see on the screen here. So I'm going to give you some background information as well as the reasoning behind the research and development of SCONE. Then I'm going to give you a high-level idea of what SCONE is trying to accomplish. Then I'm going to show you the results from the research paper. Then I'm going to show you the security of SCONE as well as its limitations. Then finally, I'm going to wrap it all up in a conclusion and show you where SCONE is today. Right, so why was SCONE developed? So it really comes down to the world of cloud and its emergence in today's world. So back in the day, physical hardware was used to maintain services and workloads. Now, obviously, as you scale a service with physical hardware, it becomes very difficult to maintain and operate, and also very expensive. So the push to virtual machines and eventually containers was enacted, where you have multiple services from different organizations running on the same physical hardware due to them all being on one server. Now, providers want to maximize the hardware utilization so they can have more tenants onto one piece of hardware because it's less expensive and allows them to utilize more of their hardware for more tenants. But the tenants also want their workloads and data to be protected from one another, obviously, because they don't want company A to be able to see protected information from company B. So the result is that multi-tenant systems are trying to aim for a balance between high performance with robust separation, because the providers of the cloud want to make sure that their servers are achieving near native performance, while the tenants are looking for that scalability and portability from the cloud environment. So a little bit more about virtual machines and containers. So a virtual machine emulates an entire operating platform. So you're basically running an independent operating system on top of the hypervisor, something like VMware or Hyper-V. Now, because it includes its own operating system, the isolation is very, very strong. One compromised virtual machine typically can't break into another at the operating system level. It comes with its downsides. To run a full operating system kernel, it usually requires more memory and storage. Also, the boot times can be from seconds to minutes, and the overhead of the hypervisor also affects performance of the VM. So historically, virtual machines were popular in data centers, but now in modern times, containers are more used. And that's because containers virtualize at the OS level instead of the hardware level. So that means that multiple containers will share the host machine's OS kernel, but each container sees its own view of the file system, processes, and network stack, things like namespaces and C groups in Linux. Now, because they don't have a full-fledged operating system, startup is usually from milliseconds to seconds, very fast compared to full VMs. They also tend to require less RAM, CPU, and general system resources than a full VM. Now, because of this, this makes containers very portable and they run consistently across various environments. They're also very resource efficient because they avoid duplicating the operating system at each workload, which leads to a higher density on each host when you're doing that. And in today's world, the ecosystem has become very, very mature with tools like Docker, Kubernetes, and Helm providing a very mature and sophisticated ecosystem for scaling, orchestration, and lifestyle management of containers. So what is Intel SGX and how does it work? Well, it uses a special enclave known as the Enclave Page Cache, or EPC, which is protected by hardware. This means that only code running inside the enclave can read or modify its memory. Enclaves can't perform system calls or privileged instructions directly. Any OS interactions must happen through outside calls or special interfaces provided by SGX. Now, this can lead to some performance constraints. For example, the enclave transitions, known as the enter and exits, are relatively expensive to the CPU. The EPC size is also limited, leading to some page swapping overhead if the working set before was very, very large. Finally, the enclave memory reads and writes have hardware level encryption and decryption overhead. But the theoretical end result of Intel SGX is that it provides some integrity of the code and data, even against a compromised OS or root user. So this is particularly suited for those scenarios where data must remain private in an untrusted environment, and especially useful for SCONE, which aims to protect containers from a compromised OS. All right, now for an overview of SCONE. All right, here's an outline of the architecture for SCONE, and I'm just going to hit on the key points here. So I/O shielding means that file systems, networks, and consoles are completely encrypted inside and out. Asynchronous system calls means that system calls are offloaded to dedicated OS threads via lock-free requests and response queues. This minimizes the expensive on-claims transitions by decoupling system calls from application threads. Then we have the MN threading model. Now, this means that multiple user level threads are mapped onto smaller OS level threads. This theoretically should improve performance by keeping threads inside the enclave longer and reducing context switches. Then we have the Docker integration, which means that SCONE containers are compatible with standard Docker workflows. Then finally, even though this is a little short, we have a minimal trusted computing base, or TCB, so only essential components run inside the enclave and reduces the attack surface because of the size of the TCB. And then in the future slides, I'll get into the details of the things in the outline here. So some of the goals of the research group included that they wanted strong isolation and protection for containerized applications regardless of the integrity of the OS. They also wanted a small and minimal TCB to limiting the code running in the enclave to reduce the attack surface. And finally, they wanted near native performance and by minimizing the overhead despite SGX's expensive enclave transactions, as well as the encryption decryption being done for the robust IO protection they wanted. Now, with those goals, there come some challenges. So they needed to figure out a way to overcome those costly enclave exits and entries. And they did that by designing asynchronous system calls. And to manage the constraints of SGX, this is regards to the resource constraints, they managed to limit the EPC size and mitigate performance penalties from the memory encryption and decryption. Finally, they needed to design a flexible threading model to reduce the context switching, and they did that by implementing the end-to-end threading scheme. So a little bit about the I/O shields. First off, you have the file system shield, which transparently encrypts file contents and protects against tampering. It does this with block level security, which means that it splits files into fixed size blocks with associated authentication tags. The end result is an ephemeral file system, which means that it is a high performance, secure, temporary storage without any heavy OS level restrictions. Then you have the network shield, which uses an in-enclave TLS termination and secure connections within the enclave to prevent some sort of like plain text exposure. Now I keep tossing this word transparent around. What does that mean? Well, that means that there's no need for any sort of external proxies or policies. All the network and all the I/O is secured directly by SCONE. But anyway, with regards to the network shield, the end result is that all network data is both encrypted and authenticated directly by SCONE. Finally, you have the console shield. It encrypts and authenticates console I/O such as standard in, standard out, standard error, and protects against eavesdropping because it maintains the confidentiality for user interactions, even in untrusted environments, because it protects from an untrusted operating system. Finally, it actually does protect against something like replay and reordering prevention because it uses unique identifiers for stream blocks to thwart any sort of attack attempts. Okay, let's start off by talking about those asynchronous system calls, right? What are those? So basically what they do is that it offloads system calls to dedicated OS threads to avoid those costly enclave transitions that SGX suffers from. And it does this by using lock-free queues to pass system call requests and responses. The end result is that it enables an enclave thread to continue executing other tasks while waiting for system call results. Then we have the MN threading model. It maps multiple enclave threads, and enclave means like user level threads, onto a smaller number of OS threads. This reduces the context switching overhead by keeping the threads inside the enclave longer, and the end result is that it should improve overall performance by efficiently scheduling work without the need for frequent enclave exits. With these two combined, it significantly minimizes the performance penalty typically associated with those SGX enclave transitions. Additionally, it enhances the scalability for multi-threaded containerized applications such as with those, 32, 64, even 128 core servers. Therefore, you have that responsiveness coming from those asynchronous system calls with an efficient resource utilization using that end-to-end threading. Finally, you have that Docker integration, Docker being a very, very popular container service. SCONE containers actually appear identical to Docker containers, which means that there shouldn't be any modifications required to the Docker engine or API. Another thing about the SCONE containers in Docker is that secure container images are built in a trusted environment. Additionally, developers, if they choose to do so, can embed security configurations and encrypt sensitive files during image creation of the SCONE container. Then you have that secure startup process. At runtime, the startup configuration is delivered securely via TLS after enclave initialization. And if enabled, remote attestation verifies the enclave before injecting any sort of secrets. Now, the integration with Docker allows for that easy adoption because it allows developers and cloud providers to leverage those existing Docker workflows and tools for image distribution and deployment. It also simplifies the transition from standard containers to secure containers without re-architecting multiple applications. Now, what is the end result for all these goals and overcoming those challenges? Well, just to give a little bit of a teaser for the results, they did manage to achieve 60% to 120% of native throughput in various benchmarks. They're using a lightweight modified C library for that minimal TCB I was talking about earlier. And finally, that seamless Docker integration because it allows for that easy adoption for anyone who wants to use a secure container such as SCONE. All right, now it's time to show you the results of SCONE. So here are the results from the research paper, which I'm going to go through with you. So figure 8, which involves throughput for latency, with Apache, which is figure 8a, glibc actually scales up to nearly 50,000 requests before latency rises significantly. SCONE async tracks glibc relatively closely, peaking around 35 to 40,000 requests with low latency. With SCONE sync, it performs well initially, but hits a ceiling around 30,000 requests, where latency spikes pretty high. With this chart, this means that the asynchronous calls from SCONE async keeps pace pretty well with the native performance because of those minimizations with costly enclave transitions, whereas the synchronous version of SCONE is more limited by those transitions. For figure 8b, which involves Redis, glibc plus STUNL goes beyond 150,000 operations per second before latency grows pretty noticeably. SCONE sync peaks pretty early at about 40,000 operations per second with a sharp latency jump. Now, if you look at SCONE async, it performs much better than SCONE sync, reaching about 100,000 to 120,000 operations per second. Unfortunately, it doesn't match the native's upper throughput. This actually may be due because Redis is largely single-threaded, so SCONE async really can't fully offload the encryption overhead to multiple threads the way STUNL can. Synchronous calls with SCONE sync incur the highest penalty due to those enclave exits on every single system call. Now with Memcached, or figure 8c, the native results with glibc plus STUNL starts to see a big latency jump past 200,000 operations per second, capping at about 240,000 operations per second. However, both SCONE async and SCONE sync both continue to scale until about 270 to 280,000 operations per second, with their latency rising more gradually. This is because Memcache is multi-threaded, and this means that it can benefit from SCONE's integrated encryption. Both SCONE async and SCONE sync actually outperform this separate STUNL process, which has its own overhead and less direct integration with the application. Now with figure 9, which relates to CPU utilization versus throughput, Let's talk about Figure 9a, which concerns Apache. glibc CPU usage grows more slowly with throughput, while SCONE async and SCONE sync use more CPU to handle that SGX overhead. What's good to note though is SCONE sync hits a very high CPU utilization at around 30,000 requests per second, the same point it had that sudden latency spike. What this could mean is that under heavy load, SCONE sync burns a little bit more CPU in frequent enclave transitions, while SCONE async is actually more efficient than SCONE sync, but still somewhat above glibc in utilization. Now with figure 9b in Redis, glibc plus tunnel consumes the most CPU overall, scaling to about 400,000 to 500% at a higher throughput. SCONE async reigns below 200 to 250% at max throughput, while SCONE sync is even lower at around 100%, but it also saturates at a lower throughput. Again, this can be attributed to Redis's single-threaded nature, which means that each solution can only drive so many operations, whereas with glibc plus tunnel, it can parallelize the encryption across multiple tunnel threads, putting the SCONE async at a disadvantage because it can only do so within the kernel module. And then you have SCONE sync, which uses one thread for both Redis logic and encryption, capping its peak throughput. Finally, figure 9c, which involves memcached. glibc plus tunnel climbs quickly at about 600% to 700% CPU utilization as throughput grows, while SCONE async and SCONE sync stay both below 600% while achieving comparable or even better throughput. Because of the multi-threaded nature of memcache, SCONE can spread the encryption workload more efficiently and causing lower overall CPU utilization and higher peak throughput than the standard external tunnel approach. Alright, now let's talk about the file system overhead. Figure 12 involves random I/O with ephemeral file system versus tempfs. You can see that the ephemeral file system outperforms tempfs and achieves notably higher throughput, especially as record sizes grow. This is because the ephemeral file system bypasses many kernel interactions, keeping most of the data operations in the user space. When encryption is enabled, which is indicated by the red squares and triangles, the throughput drops by an order of magnitude compared to the unencrypted version. While there is a drop, and that's because encryption is inherently costlier, and despite this, it actually still remains competitive with the other approaches. Now with figure 13, it's comparing SQLite SQL Cipher with the SCONE file system shield. SQLite, as indicated by the green dashed line, reaches the highest operations per second as it has no encryption overhead. SQL Cipher, on the other hand, incurs the largest performance penalty due to that block-by-block encryption that it's using, which is, I think, AES CBC. Then we have shielded SQLite, which is encrypted. This approach only slightly lags behind the encrypted SQLite, and it maintains roughly 80% of the native throughput. And this is running on SCONE's ephemeral file system. Then you have the shielded SQL Cipher. Running a SQL Cipher inside SCONE also helps, but it still performs worse than shielded SQLite because it layers SQL Cipher's own encryption on top of SCONE's shield, which increases the extra overhead. To summarize, SCONE's file system shield with that ephemeral storage is substantially faster than that classic user space encryption that something like SQL Cipher is using for larger workloads. Another thing to note is that overhead is comparatively modest, showcasing that advantage of that ephemeral file system and integrating encryption inside the enclave. Now, this all sounds great, but what are the limitations with SCONE? Well, to start, the SGX EPC is still pretty limited, so large working sets still incur a pretty frequent paging and performance overhead. Then, while SCONE can protect against some sort of compromised OS, it can't fix app-level bugs and vulnerabilities, which is something that this graph, which was compiled by Red Hat, a popular open source company, really shows, which is like nearly 59% of security vulnerabilities in Kubernetes was from a detected misconfiguration. Another thing is, some calls like fork and exec are not supported due to SGX's architectural limitations as well as SCONE's threading design. Finally, it's that trusted enclave code. Any libraries inside the enclave become part of the TCB, so if there's some sort of bugs in the libraries or code, it can completely compromise the security. And then, unfortunately, you have some limitations and vulnerabilities from SGX itself. On top of it being only exclusive to Intel CPUs, not AMD, it can be susceptible to something called a prime plus probe attack. This was discovered by an Austrian university where they developed a proof of concept that could grab RSA keys from SGX enclaves running on the same system within 5 minutes. They did propose a countermeasure, and this was published, and theoretically this should be corrected. Another potential vulnerability, which isn't exclusive to SGX, but actually Intel CPUs as a whole, is some sort of Spectre-like attack. A group at the Imperial College of London showed a proof of concept where the Spectre's execution security vulnerability can actually be adapted to attack the secure enclave. Now, since then, a security advisory and mitigation for this attack has been published and issued. And then what about an enclave attack itself? Well, researchers at the same Austrian Graz Institute of Technology from the first attack that I talked about published findings that showed, in some cases, it is possible to run malicious code from within the enclave itself. The exploit involves scanning through process memory in order to reconstruct a payload, which can then run code onto the system. And because of the confidential and protected nature of SGX, according to the paper, it's impossible for antivirus software to detect and remove the malware in the enclave. Intel actually produced a statement and they said that, hey, just run trusted code. We can't really do anything about this. And then that actually opens up the conversation and a debate about SGX, which is, does this actually enable the creation of superior malware? Some researchers at Oxford concluded that while there might be temporary zero-day vulnerabilities to abuse in the SGX ecosystem, the core principles and design features of trusted execution environments does make malware weaker than a malware in the wild. But I thought it was something interesting to note around the debate of trusted execution environments. The key takeaway from this is SGX itself isn't this end-all be-all tool behind stopping any sort of vulnerability. Because, what if some vulnerabilities arise from the tool itself? All right, let's summarize and see where SCONE is now. SCONE demonstrates that containerized apps can be shielded from a compromised operating system or hypervisor. It also shows some key techniques such as those IO shields to ensure that data remains encrypted outside the enclave. And then finally, it uses techniques such as asynchronous system calls, MN threading to achieve near native throughput for many workloads. So where's the SCONE project nowadays? Well, it's actually now a commercial production ready solution. It is now developed by SCONE, which is based in Dresden, Germany, and is a part of SCONE's confidential computing platform. It is also a major component of the German Electronic Patient Record Service, and it's also available on the Azure Marketplace in cloud-native environments. So while it's not ubiquitous and a very big commonplace in every single cloud environment, it is getting slow and steady use.